grandparents live nearby. So we go up to visit a lot, go up to Michigan football games and then stop by Zingerman's, which is always super fun.
Place.
It's the best. I know. And we get like their mail order stuff. We're so desperate for it out here in Massachusetts. So try to stay connected.
With Zingerman's?
It's this like really good deli in Ann Arbor, but they kind of do everything.
Nice.
It's a legend.
I love a good deli. Just sort of distracted by this whole GameStop thing. Have you guys seen that?
Their stock is soaring, right?
Yeah, it's unbelievable. Stay up all night watching it.
Huh.
All right, we'll go ahead and get started. So today we'll be talking about weight and balance. So what weight and balance is basically how weight is distributed on the aircraft. We have, the weight too far in the back or too far forward. We can run into some problems with the stability of the aircraft and our overall performance. So it's basically something you want to know. If you're ever on an airline flight, basically they do weight and balance every single time through their computers in the front. So they always know what their initial weight and balance is and what the weight and balance is going to be at the end. We usually don't go that far, so we just calculate the weight and balance before every flight. Some people can be kind of casual about it. They might just say, well, I know the weight and balance, what it should be. So they kind of assume they already know what it is. So yeah, weight and balance. So a bit of terminology. But probably the most important term you should know is the center of gravity. This is really what we're after. And the center of gravity is basically, the point of an object at which the weight is evenly dispersed and all sides are balanced. So it's sort of the fulcrum on which if you were able to prop the airplane up and sort of stick it on a point, the airplane would be in balance. It wouldn't fall over or anything. Both sides would be the same weight. The next term is the datum. So the datum is just an imaginary plane that the manufacturer is going to come up with. So they essentially say, hey, look, guys, we need to be able to measure where everything is from. So we're just going to create a reference point to come up with some numbers so we can do weight and balance. So theoretically, the weight, the datum can be basically anywhere. Typically, where they're going to put it is on the leading edge of the wing. And it's going to be pretty close to the CG, usually, maybe within like 30 inches. The next term is arm. So the arm is the horizontal distance from the datum to the center of gravity. Or I should say it's the horizontal distance from the datum to the object. Sorry, that's wrong. So here, if you can see in the picture, we've got an object over here in purple. The arm is right here, and we're just going to measure that distance and use it to calculate the center of gravity. The next term is moment. So moment is torque, or the rotational fork on the lever. What you can think of torque is basically, the farther away you have an object from like a fulcrum over here, the more mechanical advantage you're going to have. So you can think of this when you try to open a door, it's much easier to push on the outside of the door, far away from the hinge, than it is to push right next to the hinge. If you push right next to the hinge where the fulcrum is, you don't have a lot of moment that you can use. You don't have a lot of leverage. But as moment goes up, leverage is going to go up. So basically what we're saying is the farther away the object is from the center of gravity, the more effect it's going to have on the center of gravity. So here we've got a picture of an airplane over here. And this is just to help think about it better. We've got the datum here at the leading edge, the center of gravity in red. And when we're computing our numbers, aft of the datum is going to be positive, and forward of the datum is going to be negative. We also see two sides of the fulcrum, so the nose is going to be pulling down right here. And the elevator is going to be pulling down as well. So we got the nose pulling down. The elevator is also pulling down to help balance out that equation. So how do we calculate our center of gravity? Basically what we're going to do is we're going to have an equation called the WAM equation. And that's how we remember it. And it's basically weight times arm equals moment. So we have all of our information right here about passengers, fuel, baggage, aircraft. And we're going to find the weight for each of those. So fuel is typically going to be however many gallons you have times 6, because each gallon of fuel is going to weigh 6 pounds. So the amount of fuel here would just be 220 divided by 6, whatever that is. Baggage, yeah, we're going to include baggage here. It's going to be 30. And then the aircraft itself is going to be included in the equation. So you can think about the initial aircraft has a center of gravity, and then we just sort of add these things onto it to see how it moves. So total weight here is going to be 1,940. The first thing you want to do is make sure that it doesn't exceed your gross weight. So your maximum gross weight is basically how much weight you're allowed to have on the aircraft. Typically that's 2,300 for general aviation aircraft. Here we're 1,940, so we're well below that. In the WAM equation, we're of course calculating the moment over here. So we just take weight times the arm. Arm is going to be given to you in the pilot operating handbook by the manufacturer. So you're going to have all this information. So you get the moment, you're going to add the moment up here, and then the center of gravity is just going to be the total moment. So total moment divided by total weight. So here in this example, we have about 77,000 divided by 1,900. It's going to give us 39.59 inches aft of the datum. So if you remember before we have this datum line, we remember aft is going to be positive. So this is a positive number. So our center of gravity is going to be somewhere over here. If it were negative, it would be forward of the datum. Does that make sense to everyone? So the important thing is we're going to have an envelope given to us. Again, this is going to be given by the pilot operating handbook. And basically it's going to say for any given CG and weight, it's going to tell you whether your aircraft is good to fly. So again, you have this wide envelope. In our example, we had 39, I believe it was like 39.59. We had 1,940 for the weight. So you just come over to the weight, you dot over to the CG, and you're just going to mark in the envelope where the weight, the moment, and the CG location fall. And then it's going to tell you some information. So here it says, we're in the utility category. Utility category means we're pretty light. And that just means we're approved for some basic acrobatic maneuvers. So because we're light, we don't have a ton of weight, we're able to take, increased load. So every time we make a turn, we're adding load to the aircraft because of that centripetal force. So we can take some extra. But I mean, imagine you were over here at, 47 or 46 CG at 2,500 pounds. Really, you're getting pretty close to the envelope. You're generally not going to be approved for acrobatic maneuvers. And if you're getting this far up high, and in general, if you're close to this, generally your performance is going to be pretty limited. Remember, you have to generate lift to overcome weight. So if you have a ton of weight, you're really making your wings work harder. And that can be hard on a high density altitude day when there's just not enough air to get your aircraft to fly. So weight shifting, so this is just another equation we have that's going to tell us how the CG is going to change. In this example, we're shifting 30 pounds. So weight shifted divided by total weight, which is 1900, equals the CG over the distance the weight is shifted. So if we know how much weight we have, how much it was shifted by, and the total weight of the aircraft, we can find how much the CG is going to change by. So in this case, we've taken 30 pounds of bags and we've moved it back 20 inches. Well, this is going to move our center of gravity back 0.31 inches. So again, that's the type of calculation. Say, you flew somewhere, you dropped off to some bags, you want to see how the CG changed. It might be helpful information to know, especially if you're, again, at the edge of these, anywhere close to the edge of the envelope. So really where this matters is if we have extreme forward or aft center of gravity. And this is the question you're always asked on your check ride, is basically what are the characteristics of a forward center of gravity or aft center of gravity? And so there are kind of a few things you can sort of list off, but we'll try and understand why these things occur. So the first thing you want to know about a forward center of gravity, if the weight is moved forward, is you're going to have a really stable aircraft, especially along that longitudinal axis, basically. You see over here, if we move the center of gravity way forward, every time we get close to a stall, the tendency is for this nose to come down. And so it really wants to return to its original position, which is straight and level flight, which means it's stable. Also with the forward center of gravity, we're going to be inefficient. And basically what this means, with this extra force over here, we have to have more force pulling down the tail to balance it out. When we have more force balancing the tail, we're deflecting more air, we're creating more lift. That's going to simultaneously create drag. Anytime we deflect air, we're creating drag. Here to balance out the equation, we're deflecting more air. So we're not going to be as efficient. We're going to have a higher stall speed. So basically what this comes from is that if we pull the nose down, lift overall, because we're pulling the nose down and we have this tail force pulling down over here, we're going to have more overall force pointing down. What this means is that lift has to increase as well. And when we increase lift, we're getting closer to that critical angle of attack. So we're using up our reserves of angle of attack to create more lift because of the extra force. Last, it's harder to flare. So typically when you're flaring is when you're coming to land, you're coming down, you kind of raise the nose at the last second to land on the main wheels first. When you're doing that, you have to pull the nose up. Well, if we have all this force, if it's heavier because of this forward center of gravity, it's going to be harder to pull the nose back to flare. There's more chance you could hit the nose wheel first, which is not exactly a good thing. All right, any questions about that? All right, so we'll move on to aft center of gravity. Think about aft center of gravity, it's less stable. So it's an unstable aircraft. Before we had forward center of gravity, the nose wants to come down. But when we move the center of gravity back, well, there's not as much force over here pulling the nose down to get it back to straight and level flight. Also, we have less tail force over here, which basically means it's easier to move the nose of the aircraft because we don't have so much weight, force pulling down here. Another way that it's less stable is it's easier to turn. So in a turn, you essentially have to bring the nose of the aircraft around. Well, when the nose doesn't weigh as much, it's easier to move the nose of the aircraft and get it into a steep roll. With an aft center of gravity, we're more efficient, and that's basically because we're creating less tail force. We don't have as much to balance out, and that's going to create less drag overall. Finally, we have a lower stall speed, and again, that's because we've moved the center of gravity back. This has less moment, so again, we're getting closer to the hinge. It has less effect. We have the less tail force, so less force pulling down overall. So this is less. So we don't need as much lift to keep the aircraft in the air, which means less angle of attack. So basically, most of the aircraft that you're going to find general aviation are going to be forward center of gravity. They're going to be super stable. Aircraft that have aft center of gravity tend to be more acrobatic and really maneuverable. So when you want maneuverability, you should move the center of gravity back. But at the same time, when you move the center of gravity back, it's not as safe. You're potentially jeopardizing, if you get in a bad situation, not being able to recover because the aircraft is not as stable. If you guys have ever seen Top Gun, the scene where whatever his name is, Tom Cruise's RSO or whatever dies, they got in a flat spin. And the reason they were in a flat spin is because the F-14, has an aft center of gravity. It's hard to recover from a spin because, again, the nose isn't pulling forward as much to pitch the aircraft down. So again, this is the stability versus instability. And if you think of at the F-16 right here, really what it prizes maneuverability, because when you're in a dogfight, really the name of the game is to get on the tail of your opponent and shoot him down. Well, the only way to do that is by increasing your turn rate or decreasing your turn radius. So you have to be super maneuverable. And in the case with an F-16 or an F-14 or an F-18, we're going to have negative stability, which basically means the center of gravity is going to be back from the center of lift. If the center of gravity is behind the center of lift, well, we don't even need the tail force pulling down over here to balance it out, because we've already got the center of gravity on this side. So this makes the aircraft super maneuverable, super easy to turn. You can really do whatever you want. The problem is with negative stability is that the aircraft is really, really unstable. So if the pilot were directly controlling the flight controls, they wouldn't be able to control the aircraft at all. In fact, they have to use something called a flight control computer system to basically fly the aircraft for them. So when they input a flight control, they're basically just telling the computer what to do, and then the computer is going to input that to the ailerons, the stabilator, or the rudder. If this system were to shut off, the aircraft would be too unstable. The pilot would actually have to eject if they didn't have the computer there helping them. This is also known as a fly-by-wire system. So fly-by-wire. I guess an interesting fact is that that's the main difference between Airbus and Boeing. Is that Airbus uses this fly-by-wire system in all of their aircraft. So essentially they have the computer helping the pilot out with the flight controls, whereas Boeing tends to give pilots more control. So that's sort of the difference in philosophy there. Any questions at all? Cool. So that's it was a short section. It's chapter 10, and then this is the question I have for you guys is, given all this information, how far aft of the datum is the center of gravity? So I just want you guys to calculate the center of gravity, and the weight here is 180. So I just put 30 times 6 to show that the fuel weighs 6 pounds and you have 30 gallons. So I'll give you guys a few minutes to work this out. All right, I'll go ahead and work through this. So we just need the total weight divided by the total moments. So we just need the 2 moments right here. So that's 380 times 64 is 24,320. 180 times 96 is just 17,280. Add these all up. 51,593. You get 193,193, I think, divided by the total weight, which is 1495 plus 380 plus 180. Oops. I believe it's 2,055, I think. 193 divided by 193. So I believe I got 94 inches, 94.0 inches aft. I'll double check this. I'm sure whatever you guys got was probably correct too. So yeah, it's gonna be about 94 inches. So pretty easy. You just write them all out in the list and add up the weight divided by the moment. You got your center of gravity. See whether that's in the envelope, and if it's far aft, you know that your aircraft is going to be kind of unstable but maneuverable. If it's far forward, it's going to be stable but kind of heavy and inefficient. So that's all I got for you guys. Any questions about that?
Just a quick question. Would it be 2,055 over the numerator?
Oh, yeah.
That's weight. Is that why the aft is so off?
Let's see. Yeah, I think I just sorry. Did I miss right? Is it moment? Yeah, I think it should be moment over weight.
Mm-hmm.
So my bad with that.
That's all good.
Cool. Let me just, yeah, total moment over total weight. All right. Stop sharing. That's all I got for you guys. Thanks for coming. And next week we'll just we'll do ATC, which is air traffic control and airspace. We'll do weather and navigation, and then we'll be done. So hope to see you guys soon.
Thanks, Alex.
Yep.
Thank you.
Thank you.